Hi everyone, and welcome to Eric's Electronics Workbench. So on the bench today I have this Simpson Model 260 Series 4 volt-ohm milliamp meter. And this meter has developed a problem with the accuracy when measuring DC voltages. So let's get started with the troubleshooting. Alright, so this very nice looking Simpson Model 260 Series 4 meter dates from probably the late 60s or early 70s from what the previous owner was telling me. He said he purchased it new about that time period. It also came with this original instruction manual. Nice to have that. You can see in the front right here there's a copyright 1964. And in the back the manual has, let me see if I can find it here, yep, there's the schematic. So we'll take a closer look at that schematic in just a little bit after I do some troubleshooting. Now, if you're not familiar with how these meters function, there's basically a whole bunch of resistors inside that scale the input that you apply to the various jacks on the front panel down to a very small current flow that goes through the meter movement. Now these meters do have batteries in them, and the batteries are only used in the ohms function. All of the other measurements that the meter is able to take don't use the batteries. There's no active components, anything like that. And there's just one capacitor inside the unit, and it's between the positive jack and this output jack. It's for measuring an AC voltage when you have a DC voltage on it as well, when you want to block that DC voltage. So very ingenious design, how they're made, very accurate meters, known to be rugged and very long lasting. But unfortunately this meter, as I mentioned, has developed a problem in the DC ranges, and the accuracy is suffering quite a bit. Now, the AC voltage measurements seem to be very accurate. I'm not seeing any issue on that. I did power up the meter and verified that part is working okay, and the other functions are working very well. But the DC voltage is definitely having an issue. Now, there's really two ways that we can go about troubleshooting the meter. We could apply DC voltages to the meter and then look at the schematic and try and figure out, why it's not working based on what we're seeing happen. But another way is to take some resistance measurements at some of the jacks on the front panel. And with the resistance values that we see, we'll take a look at the schematic and see how those resistance values compare. And that's what I'm going to do. And I think when you see the schematic, it'll make sense why that's such a straightforward way to do this troubleshooting. And I think it'll zero in very quickly to where the problem is at. Now I will apply a voltage in just a moment to one part here just to verify the accuracy of the meter movement, because all of the ranges and all of the measurements rely on a resistor that is across the meter movement and also in series with the meter movement. There's a calibration circuit there. We want to make sure that that's correct because that's sort of the starting point of everything. I'll show you that on the schematic as well. So let's go ahead and start with that measurement first. So that measurement would be taken from the common terminal right here over to where it says 50 microamps. And yes, 50 microamps, a very, very small current. And 50 microamps will give a full-scale deflection, all right? So you have to be very cautious. This is basically putting a connection directly into the meter movement, and there's no protection in this meter. Later series of these meters did have some protection diodes that were back-to-back across the meter movement. This doesn't actually have that. And I should mention there's no active components in the meter. There are two diodes for the rectification on the AC ranges. So let's turn this selector switch right here to where it says 50 volts and then it says microamps. Okay, so that's the position that you want for the common over to the 50 microamp position there. And I'm going to take a resistance measurement, and there should be 5,000 ohms or very, very close to it between those 2 points. Now, this meter, if you don't make any adjustments on my ohm meter over here, it will actually peg this full scale. Way too much voltage will come out of here. So we actually need to put this into the auto range. So first of all, go to resistance mode and take it out of auto and go into the manual mode. And you can actually see here, I think you can see on the camera, the current values that are underneath right here. So like this says about 100 microamps, 10 microamps, and so forth. So it's very handy that they actually tell you about what current will come out of this meter in these different ranges. And you can see right here, it's about 1 milliamp, and of course this is 50 microamps, so the wrong range would peg this over all the way. So we'll go right here where it says about 10 microamps. So we're not so interested in what this reads on here as much as the actual resistance value across here. So if I go from here, like so, and we do have a deflection on the meter, and our value is looking really good. So 4.991 for 5 k ohms right there. I mean, that's right on. You really couldn't ask for that to be much closer. Just if I wiggle the probes around there, it jumped a little bit, but Yeah, that's looking really good. No issues with that. 4.99. So I'm not seeing any problems with that part of the meter. And that actually makes sense because the AC voltages looked okay. So if that part of the circuitry was having a problem, it would affect the other ranges as well. Now, one other thing that I want to do is I'm going to apply a voltage across here, because you can put a voltage between the common and the 50 microamps and up to 250 millivolts, and 250 millivolts will deflect full scale, and at that point you're actually getting also 50 microamps. So let me go to my voltage calibrator, take a look here. I'll swing the camera up to that. I can't put everything in the shot, but I'll show you the calibrator that I'm going to use, and then I'll make the connection over to the meter, and let's just make sure that the meter does read exactly what the calibrator is putting out. So let me move the camera real quick here. All right, just to verify the meter movement's accuracy, I'll be using my EDC model 522 RA7 DC voltage and current calibrator. Now, this instrument's been calibrated, it's known to be very, very accurate, but I'll be using it on the voltage output, not on the constant current output, but either one could actually be used, because remember, on the meter's 50 microamp input, at 50 microamps, that's the same full-scale deflection you get if you apply 250 millivolts, so we'll just be applying that voltage. So if I turn the meter on like so, you can see this is the decimal point right here, so that would be 100 microvolts. If I go like that, that's 100 millivolts. And I'll plug my test leads in on these jacks over here, and I'll put the camera back down on the meter and zoom things in a little bit so you can see exactly the measurements and the readings on the meter, and we'll continue on. All right, the calibrator's DC voltage is connected to the Simpson 260, so I have the positive right here on the 50 microamp jack, and the negative right here is going to the common. And then my digital multimeter is connected with this probe on the positive and the probe right here on the negative, just to monitor that voltage. So you can see it is sitting right at 100 millivolts DC. That's exactly what the calibrator is set to. And the Simpson 260 is indicating correctly, so that's a good sign. This we're reading on the top scale, so 0, 50, 100, 150, 200, and 250, and that's read as millivolts DC. So again, we're at 100, and it's pointing right at 100. It's exactly on that tick mark. So that looks very, very good. Now, I should also mention that before I set this up, I did check this zero adjust right here, just a little adjustment, and this sets the resting point of the needle so that it's right on the zero mark over here. If this is not set correctly and this is above or below zero when there's no input, then all the calibration would be off. So it's definitely something you have to check before you start with anything else. So that looks very good. Let me just increase this to 200 millivolts. So we'll go like so. So there's 200 millivolts on the calibrator, and yeah, that looks really good. It's right on that 200. It's perfect right there. So I'm not seeing any issue whatsoever with the meter movement itself or the resistors that are right around that movement. And we'll take a look on the schematic and you'll see those components and why this is a good starting point, but it's looking good so far. So let's look at the multiplier resistors next, and we can do that right from the front panel. So I'll reposition things a little bit here and we'll take some more measurements. Okay, the next thing that I need to do is to check the DC voltage multiplier resistors. So we can do that right from the front panel. And basically you just need to have this on positive DC, but it could also be on the negative DC. That's just like flipping the polarity. You don't want it on AC because that would select an entirely different set of multiplier resistors, and the AC ranges are working okay. So leaving this on positive DC, and we'll start on 5,000 and work our way all the way down to 2.5 volts. So if I go over here, 5,000, and on the meter, my digital multimeter, I put this on ohms over here, and it actually needs to back on auto ranging. All right, there we go. So this meter has 20,000 ohms per volt specification. So what that means is that you take the voltage range, so starting on 5,000 volts, multiply 5,000 times 20,000, you get 100 million. So there should be 100 million ohms between this jack and common. So let's take a look, start with that. And we're getting a little bit more than that, so that's in gigaohms, so that's 0.107 gigaohms, so that's 107 million ohms. So ideally that should be closer just to 100 million ohms, but it looks like it's reading a little bit on the high side. So we'll keep that in mind, but let's go to the next range. So we're not going to change this. This just stays on for 1,000 volts. You just come over here and go right across these terminal jacks instead. So 1,000 times 20,000 is 20 megohms, all right? And little bit high there, 23 megohms looks like. So we'll keep that in mind. That's also out of spec. 250 volts, so 250 times 20,000 should be 5 million, 5 megohms. Almost 7 megohms. Yeah, that is 7 megohms. So that's out of spec. That doesn't look right. Nope, that's not right. So we go to 50. So 50 times 20,000 is 1 million. So it should be 1 megohm across here now. Oh wow, that's almost double, almost triple. 2.7. Yeah, I mean 2.8. That's way up. That's way out of spec. So what that means is that there would be too much voltage dropping across that multiplier resistor, and this is going to be very, very inaccurate. Let's go to 10 volts. See what we have here. So you can actually see an indication now because the ohm meter is putting a voltage out, so we can actually see an indication up there. So what do we see now? That actually doesn't look too far off. So that's 0.202 megohms, which is 202 kiloohms. And 10 volts times 20,000 should be 200 k ohms. So that's really not bad. That looks pretty good. It is up just a little bit, but if they used a 1% resistor, I imagine, it's not too far off. So that's not too bad. And 2.5. That looks really close. So 2.5 times 20,000 should be 50 k ohms, 50,000. And you can see on the meter there, 50.3 k ohms. So that looks like that's within spec. I don't see any issue there. That's very, very close. So given that this meter, you know, is probably from the late 60s or early 70s, the resistors, yes, they are probably going to have drifted some. So having that 50 k ohms, you know, up a little bit there, not a big deal. Probably still within spec and very usable. But there's something going on. If we go back to that 50 volt range again, so 2.5 and 10 look good, but we hit the 50. Yeah, that's way up. That should only be 1 megohm. So let's take a look at the schematic and see what that means when these ranges look good, but starting at 50 and going above looks like a problem. So let me grab the schematic and we'll take a look. Okay, let's take a look at the schematic so we can better understand where the problem is based on the tests that I just did. So a couple things to note on the schematic. First of all, this switch right here, these 3 sections, you can see this little dashed line. That just means that those are all ganged together. They all move in unison. So this is negative DC, positive DC, and AC. So I had this on the positive DC setting right there. So you can think of a jumper being across that middle point. And then the range selector switch, all of this switching up here, all moves in unison. You can see that dashed line going right there. All right. Now, this is the rectifier bridge for AC voltage and the multiplier resistors for AC voltage. AC is working correctly, so there's no issues going on over here. There's a potentiometer there, potentiometer here for some calibration. There's a current shunt right here. There's some resistors right here for the ohms function, batteries for the ohms function, some current shunts over here for the small current ranges. The meter movement itself right there, adjustable resistor there and right there. We'll take a closer look at those in a moment. And then these are the multiplier resistors for the DC voltage. We'll take a look at that. Now, the first test that I did with the 5,000 ohms, when we took that reading, let's take a look at the path that the circuit takes for that reading and see why that was so important. So starting at 50 microamps, that's where I was taking the reading from that over to the common right here. So if we go up here, this path comes over, comes up this long common side of the switch, comes over here. The meter movement right here, you can see it says calibrated to 5,000 ohms, so that's why that's an important value. We have a 200,000 ohm potentiometer in parallel with the meter movement, and then a 5,000 ohm potentiometer in series with this parallel combination. So these are all calibrated and then just left alone, and this calibration affects the entire meter's accuracy. So very important that this be set correctly. So the path comes over here. Now remember, this was set down here on the position number 3. It was on the 50 microamp position, also shares with 50 volts, so position 3. So that just jumps across right here, comes down this side, comes down right here, has 2 places it can go, right here, This was in fact in the middle position because it was on DC volts, and there we are at common, so that completes the circuit. This path coming over here went up to the top, but it's not complete. This was shifted down to positive DC, so no, that's not connected. So that 5,000 ohms, again, it's so important to get that measurement because that shows that this is set correctly, and that was looking very good. So then moving on to the multiplier resistors, those are right here. So starting on the 1,000 volt, that's this jumper across right here. So we go from the positive input, and we should have been seeing, if we go over here to the 1,000 volts, it was 20 megohms, okay? So we should have seen 20 megohms. We actually saw something higher than that. And go from positive right here, come over here, through this middle point because it's on positive DC, come up here, over, all the way up here, 1,000 volts through this jumper. And then right here, we have a 15 megohm resistor. It goes through that. There's no connection on any of these, so that's not going anywhere. So we have a long series connection, 15 megohms, 4 megohms, 800,000 ohms, 150,000 ohms, and then 45,000 ohms. And then we're over to this part of the switch, come back up here, over, down, and then through this meter, which is 5,000 ohms. So if you add 5,000 ohms and all of this previous resistance, you should get 20 megohms. And then you're on the other side right here. This comes up, comes down here, comes over. Here's that connection, which can go over this way, which goes nowhere because it was not connected. Comes down, it is connected right here because we're on positive DC, and out to the common jack. So that's the path that the voltage will always take when you're taking the voltage reading, so we don't need to retrace that for every combination as the switch moves. So we can see what happens over here. This shifts down, so at 250 volts we were getting a higher resistance than we wanted to see, and at 50 volts we were getting a higher resistance than we should have. In fact, it was very high in 50 volts. Well, what does that tell us? That tells us that this resistor starting right here is probably no good, okay? That looks like R8 on the schematic, 800,000 ohms, because 50 volts had a very high reading, okay? So if this resistor has shifted up in value, the 50 volts will certainly go up. But we know that the 10 volts actually was okay. It was very, very close, and 2.5 volts was okay. Well, 2.5 volts just goes right across. It actually doesn't go through this resistor string up here. It just goes through this 45 k ohm, and then some of the, the rest of the circuit over here. And then when we go over here to the 10 volts, that uses the first multiplier resistor, and that worked okay. So we know this resistor is good, this resistor is good, and everything over here in the meter circuit is good. But when we hit 50 volts, again, a problem, and that first resistor that would be an issue and a concern is this R8, which is 800 k ohm or 800,000 ohms. So I think this is the place we need to start. Now, unfortunately, 800,000 ohms is not a standard value. Resistors tend to go in standard increments. So I'm not sure if that's something that I'm going to have here or that would be readily available, but that resistor could be made from either resistors in series or in parallel. So I think that's a starting point. We need to take a look at that. Now we can measure that resistor right on the circuit board. I can do that next, just to verify it, but I think that's the starting point. And I think it would be good to change that resistor first and then see if these values come back, where they're supposed to be. We could also measure across them in the meter, but this definitely looks like the starting point, because with this resistor bad, it's going to affect the value as we read up here because it goes through this resistor. And on the 5,000 volt setting, that multiplier resistor is down here. You can see DC 5,000 volts right here. You can see there's a 80 megohm resistor, very high value, actually 2 watt, 80 megohm right there. And then that just comes over here, and then where your positive jack right here comes in, see it all shares this common connection, comes up to the switch. So it's just adding this 80 megohm resistor in series with ultimately all of this up here, okay? So that's how that part of the circuit works to multiply and allow you to measure higher and higher voltages. It's basically just dropping more and more voltage across these resistors. All right, so the next thing that I'll do is open up the meter, and let's take a look at this R8 and see what value it actually measures at. Okay, I had the Simpson 260 opened up, so we have access to the circuit board, and R8 is this resistor right here, conveniently located at the edge of the board, so easy to get to. So let's take a reading on this resistor, see what we have here. And whoa, yeah, that's way off. So 2.29, 2.3 megohms. That's way, way off. So that should be an 800 k ohm or 800,000 ohm resistor. That's really drifted. So yeah, no wonder the DC voltage, ranges 50 volts and above, we're having problems. That resistor is way out of spec. Now, something else that you need to check here. Let's go try one side down to the input jack, and oops, slip off there. Yep, we do have connection there, no issues with that. So I have the main selector switch on the 50 volt range. So there's a connection from the positive input jack up to this resistor, and it is making connection there, no problems. So the routing through the switches is perfectly fine. No excessive resistance going on with any of the switch contacts, but just across this resistor, that is showing that resistor is way, way out of spec. So let me see what I can do about that. 800 k ohms is not a standard value. Resistors tend to increment in standard values when you go to companies like DigiKey or Mouser and order resistors. If you're doing a big production run and you're a manufacturer, sure, you can get resistors manufactured to pretty much any value that you would need. But 800 k ohm is not something that you typically find. So the only way to get to this value now is probably going to be to either connect two resistors in parallel or two resistors in series. So let me go through my resistors and see what I have. If I have an 800 k ohm or can find that, that would be very simple, but I'm not so sure that that's something that I can come up with. So let me do some checking, and I'll be back when I have some options here and how we can proceed. Alright, so I was not able to find an exact 800 k ohm resistor. However, I did find a couple different options for possible replacements, so let's take a look. So one possibility is to parallel these two resistors. This is a 1.2 meg ohm resistor, this is a 2.4 meg ohm resistor. Each one is rated half watt at 1% tolerance. Now the original resistor was a 1% tolerance, and it's important in a circuit like this not to increase that tolerance. You wouldn't want to replace these with, say, 5% tolerance, because the tolerance is the amount of change that the resistor might have, so these could vary 1% up or down in their value. And if they change excessively, then that changes the accuracy of the meter. So paralleling these is one option, and the other option is to connect these two in series. These are 400 k ohm resistors, and they're rated 1 watt at 0.1%. So these have a better tolerance, just 0.1%. I like the idea of using these. We'll have to see which of this combinations fits better on the circuit board, but this definitely has a better tolerance, so that would be an improvement. And these are rated 1 watt, so a little bit of safety margin. Again, these are half watt, and the original was a half watt, so these are equivalent in that wattage rating. And when you're replacing resistors, you don't want to decrease the wattage rating, say a quarter watt or something like that would not be suitable for the circuit. Now, a quick Electronics 101 lesson if you're new to electronics. When you connect resistors in series, you're just adding up the total, and that becomes the resistance value. So this is 400 k ohm, 400 k ohm. When they're connected like so in series, all right, across there, then this becomes 800 k ohms across that total. When you parallel resistors, whatever the lowest value is, so here we have 1.2 meg ohms, the total across here, when these are paralleled together, electrically connected from side to side, the total resistance will be something less than whichever resistor has the lowest value. So 1.2 meg ohms, this is 2.4 meg ohms, and the total 800 k ohms, which of course is less than the 1.2 meg ohms. If you have two resistors of equal value, for example, if we were to parallel these two, okay, this is 400k, 400k, it's just half, so this would be a 200k ohms across there. So that's always easy to figure out if they're equal value. But when they're not the same value, there's a mathematical formula that you can use to figure out what the actual value will be. I'll put that up on the screen now. You can pause the video if you're interested in that. But there are apps you can use on your phone that can figure out parallel resistors, and there's online calculators as well. So as a quick demonstration here, I'll just connect these to my ohm meter. You can see the actual readings here. So I'll go like so. Should be making connection there. All right, so those are electrically in parallel, and you can see we do have 800 k ohms. So 802, but that's within spec. 1% of 800,000 would be 8,000, so this could change by as much as 8,000 ohms up or down, and there is no problem there. That is within spec for that 1%. And if we go over here to these, so, and what I need to do is grab my jumper wire here and just connect this in the middle. Alright, so you can see that's just connecting those two resistors like so. They're in series. And we're exactly on 800k ohms. That looks really good. I like that reading better. That has a, the tolerance is better, just 0.1%. That's closer to 800k than the parallel combination. So again, I like using this series combination. So let's take a look at the circuit board and see which combination would fit better on the board. And let me reposition things a little bit here and we'll take a look. All right, for the two resistors in series, so if I take the resistor and connect them like this, or I can connect them just sort of back to back in a straight line like so. Just trim the leads down and make the solder connection just very, very close right in there. And then this being the defective resistor right here, it looks like if they're connected very close back to back, the length from the end here to the end of this resistor will fit within the sort of the footprint of this original resistor, the hole in the circuit board on each end there. So that looks like a good possibility. I think that will work well. Now if you go like this with these two in parallel, of course it's not a problem for the length. They would fit across there. There's room on the board, no problem like that. And the one resistor could go down into the hole and the other resistor could solder up on the top side there. So it looks like either one would fit on the board without any issue. So I'm going to go ahead and go with the two resistors in series. I like the specifications of those resistors better. So let me desolder this resistor and get the new ones installed, and then we'll continue. All right, the defective 800k ohm resistor has been removed, and the two new 400k ohm resistors in series are installed. So they fit in position right there, no problems. So let me grab the case over here and I'll just set the meter back down in here. And let's take some measurements. So the 50 volt position is the position that was affected by that resistor. So grab my test leads here and let's go across from common to the positive terminal right there. Hey, look at that. Not too bad. So it's right at 1 megohm. Very, very close to 1 megohm anyways. That's exactly what it should be. So that's looking very good now. So on the 50 volt position, no issues with that. Double check on 10 volts. Still looking good there. Very close to that 200k. Just up a little bit there, but really probably not going to be an issue. And 2.5 volts. Yep, very, very close to the 50k, all as before. Now let's go back up to the 250 volt range and take a look here. That it looks like that's still out of spec. So that should be 5 megohms, and we're almost 356 k ohms high. So that's looking like that's out of spec. Let's go to the 1000 volt position right here. Yeah, that should be 20 megohms, and we're about a megohm high on that. So that doesn't look right. That looks like there's going to be some problems still on those ranges. So let's grab the schematic here. So it looks like if we go back up here again, the 250 volt range, that's going to be affected by this 4 megohm resistor, and then the 1000 volt range has this 15 megohm resistor. So the resistor that was just replaced is this 800k ohm. So we know these are in series, and as we go up in the ranges here, it's just building with more and more resistance in series. However, 4 megohm and 15 megohm, I know I definitely don't have those values here because I just went through all my resistors to locate this 800k, so I know for a fact I don't have anything up in this range. So I'm going to have to do some checking around and see if I can locate those resistors, maybe at Mouser or DigiKey, something like that. Hopefully one of those companies will have those resistors. So it looks like there will be a part 2 on this because I'm going to need to order those in. So we'll stop the repair at this point, and then when I have the resistors, part 2 video will be posted. So if you're enjoying this video and the videos on this channel, please remember to subscribe, and if you like this video, please remember to give it a thumbs up. So until next time, take care. Goodbye for now.